Hello, in this lecture I am going to derive the Navier-Stokes equation. Navier-Stokes equation. Navier-Stokes. So Navier-Stokes equation is basically the momentum equation by considering viscous. So I'll be deriving this Navier-Stokes equation by starting from Reynolds transport theorem. The Reynolds transport theorem talks about the rate of change of an extensive property. Of a system. So extensive property is an integral quantity of the system, and we can have different examples of extensive property. The mass of the system is an extensive property. Momentum of the total momentum of the system is an extensive property. So for deriving the Reynolds Navier-Stokes equation, we take the extensive property as momentum. So momentum. So momentum P is equal to mass into velocity. So for using the Reynolds transport theorem, we have to have an extensive property and the corresponding intensive property. And here U is intensive property. The corresponding to M, that intensive property is the mass per volume. So B M by V into U. This is going to be for a point. This is going to be the density at that location. So sorry, this is not capital D, but this is the intensive property. The corresponding intensive property is denoted by small d. So this is the corresponding intensive property. And the Reynolds transport theorem is dV by dt of the system is equal to integral over the control volume dou B by dou T dV plus integral over the control volume surface B U dot N ds. This is velocity. B is the intensive property, that is here it is rho U. And this is a rate of change of momentum of the system. Rate of change of momentum of the system, and that is nothing but the force acting on the system. That is by Newton's second law. This is the force acting on the system, and that is integral over the control volume dou by dou T of rho U dV. This is volume plus integral over the surface rho U dot N ds. This rho U together becomes the dyadic tensor product. So this is a tensor product. So these two things together is a tensor product. So the force acting on the system. So fluid system. So in Euler equation, the force on the left hand side, this force is considered as the force due to static pressure. So suppose we are having a fluid system, a well-defined boundary. The static pressure will be acting normal to any point. Static pressure will be acting normally into the system, inside into the system. That is opposite to outward normal. If n is the outward normal, it will be acting in the minus n direction, minus n cap direction into the magnitude of the or the intensity of the pressure. That is the magnitude. So P into N cap minus. So that is the intensity of that is force by unit area. It's a surface force. Surface force. And for this system, if you want to calculate the total surface force, so that will be the force acting on the system due to the static pressure. So for that, we have to do the integration. Integral over the surface, integral over the surface of the control surface enclosing the system. That is the integral over S minus N minus N P ds. So, so instead of the force acting on the system, if we take this alone, it's going to be the finally will be resulting. The resulting equation will be is called Euler equation. So, Navier has considered the force due to viscous stresses also. Thereby, the Navier-Stokes equation. For that, he has used the Stokes relations. Now, let us for this derivation, let us restrict ourselves to incompressible flows. So the fluid has a velocity and the velocity gradient. Velocity gradient results into the change in the shape of the fluid system. So velocity gradient causes a change in the shape of the fluid system. So, so there is what is called the gradient of velocity is del u. And we can see through physical interpretation that this del u is the velocity gradient plus del u transpose half of this, which is the symmetric part of the del u tensor that gives the strain rate epsilon. So the strain rate epsilon is equal to half the gradient of velocity plus del u transpose. So this can be easily seen that there is a diagonal elements of this epsilon tensor. This is the tensor called the strain rate tensor. Strain rate tensor. So diagonal elements of epsilon represents the normal strain, and off diagonal elements gives the shear strains in the respective planes, depending upon the coordinate system you use. So this is what is called the strain rate tensor, and the Stokes relations gives the relation gives how the strain rate is related to stress. So that is stress. So stress is the resisting force per unit area. So there's a strain is there. So correspondingly, there will be a resisting force per unit area that is called stress, and that is given by Stokes relation gives this stress. So is the stress is equal to Q mu epsilon for incompressible flow. For incompressible flow. So incompressible flows, the Stokes relations that connect the stress with the strain rate is tau is equal to mu epsilon. So, in addition to the static pressure, we are now considering the viscous stress also on the surface of the system. So, any point, there is a any point on the surface of the system or inside, we can define what is called the whole viscous stress tensor, and that will be varying from one point to another point on the system boundary. It will vary. So what we do is, since it is varying, so we have to calculate the force corresponding to the stress. So for that, let us consider a small surface area ds, having a unit normal n. So the Cauchy's relation for the force, or the force, or the stress vector, the force per unit area, stress vector on this small ds is n dot tau. This is a Cauchy's equation. So this is a stress vector. So stress vector into ds gives the force vector. This is a force. This is a force on the resisting force on ds, and integrate over the entire surface of the bounding surface of the system. This gives the total force acting on the system boundary due to viscous stresses. So this is the additional term which Navier has considered for developing the Navier-Stokes equation. So now the total force has this part, and earlier we have derived this one. So the total is can be written as integral over the surface static pressure n with the negative sign ds plus integral over the surface n dot tau ds. This is equal to integral over the volume dou rho u by dou t plus dv plus integral over the surface rho u dot n ds. So this is the condition. Okay. Now we have to do some manipulation or changes. So that surface integrals are there are three surface integrals. We convert the surface integral also into this kind of volume integral, so that the entire equation is in volume integral. So for that we use Gauss divergence theorem. Gauss divergence. So integral over the surface minus p n ds, that becomes integral over the volume by Gauss divergence theorem. Minus is there, then del p. So minus pn del p d. So that is kind. So minus okay, del p dv is equal to pn ds. So actually we should have something like a quantity, that is a scalar quantity multiplied by a vector, that becomes del of that scalar quantity, or if it is a vector quantity, that vector quantity or tens other higher order quantity dot n. So here n dot tau is there, so that has to be changed the first. So we can write as tau transpose dot n ds. So this n dot, that is pre-dotting, if you do, that is a tensor, then if you transpose this and then pose dot n also same. So tau transpose n ds. We will not change this surface integral now. We'll take one more step for doing that. Dou A by dou T of rho u dv plus, so this is u dot n ds kind of thing. So the entire, this is as a tensor dot n, so we don't have to do anything. So we can change this something dot n ds, that becomes integral over the volume del dot rho u u. This is what is Gauss divergence theorem. So some vector dot n or a tensor dot n ds, that becomes del dot of the tensor dv or del dot of the tensor dv or del dot of that vector dv. So if this is a tensor, then this del dot becomes a vector. If okay, it is like this integral over the surface f dot n ds, where f is a vector, becomes integral over the volume del dot f dv. So in which case, this, since is a vector, it becomes a scalar. If this is a tensor, it becomes a vector. So like that. So now this also will change. So it becomes, I will take this to next thing. Okay. So now that we can change this also by Gauss divergence theorem. So integral for the control volume plus, this is also integral of the control volume del dot tau transpose dv is equal to, so if this, because of incompressibility, we can take rho outside also, integral over volume rho dou by dou t of u dv plus integral over the volume rho into del dot u u e. So okay. Now that we can take everything, so this side there is a volume integral, we can combine them. So del dot tau minus del t dv equal to integral over the volume. If the rho can be taken outside, dou u by dou t plus del dot u u and v. So here we are having a volume integral, here we are having a volume integral. So this is a volume integral over a particular volume. So this equation is applicable for any kind of volume. It can be a small volume or a very high volume. So by applying this to an infinitesimally small volume, we can integrate these integrals. That is what is the application of this integral equation. The small volume leads to equating the integrals, because we are having both side volume integrals. So on very small control volumes, infinitesimally small control volumes, we can say that. Okay, this rho can be taken off this side. Dou u by dou t. These terms are in actually the terms are accelerations. Actually, this left hand side force per unit mass, and this side is acceleration. Some kind of acceleration. So this is what is now that to finally derive the Navier-Stokes equation, we need to only substitute for tau transpose here. That is use Stokes relation. In Stokes relation, is tau is equal to mu into del u plus del u transpose. So tau transpose will also be same, because tau transpose is going to be this one. This the whole transpose that this will go. So that is same as tau itself. So now that let us do the del dot. So del dot of tau transpose is 2 mu if you are seeing constant del dot del u transpose plus del u. So okay, okay. This can be easily worked. This can be easily worked. Just write del of u and make the simplification. So a better method of doing that is by writing the components or in terms of index using index notation. So by index notation, so this is 2 del dot. This you can write that dou ui by dou xi, dou ui by dou xj. If this is a del u transpose, okay, del u is dou ui by dou xj, then del u transpose will be dou uj by dou x. So, del dot transpose is 2 mu. So this is actually a tensor. This is actually a tensor. So these terms are tensors. So dou by. So finally we want a vector having a component and the ith component. So this del dot is going to be 2 mu dou by dou xj. Or so dou u I by dou xj plus dou uj by dou x. So that is 2 mu. No, but so what happens is that actually actually the result is a resulting thing is a vector. So we are having the tensors. So one index should go and the other index should be free. So one will be a dummy index. So the j is the index which is a dummy index. So that will be varied and summation is done so that the I index will remain. So that the entire del dot transpose will be it will be written in terms of a component that is actually the ith component of it will be the ith component of del dot tau transpose. So because this here dou by dou xj is used. So we have used dou by dou xj. So j index will go on summation I will present. So here also j index will go on summation I will present. So that is what. So this dotting is obtained by operating dou by dou xj. Is not exactly del dot tau transpose, but ith component. ith component. ith component. So 2 mu. So dou by dou xj we can operate. So this is going to be dou by dou xj, dou by dou xj of dou ui by dou xj. That is dou squared ui by dou xj squared, or dou xj dou xj. That is the second derivative of the ith component of u. Ith component of u. Second derivative of ith component. Actually, dou squared ui by dou ui by dou x1 squared plus dou x2 squared plus dou x3 squared. So j will be varied and summation is done. Plus here actually there is an xj is there, xj is there. So dou ui by dou xj is differentiated with respect xi is differentiated with respect to xj. So dou by dou xj of dou uj by dou xi. So this is again 2 mu into dou squared ui by dou xj plus actually this is xj out and xi inner derivative is with respect to xi and outer derivative is with respect to xj. So that can be interchanged. We can write dou by dou xi of dou uj by dou xj. So this is actually dou u1 by dou x1 plus dou u2 by dou x2 plus dou u3 by dou x3. And our normal notation is this u1 is u itself. The u2 is the second component. In Cartesian it is v. And this u3 is our notation is w. And x1 is x itself, x1 is x itself, x2 is v and x3 is z. So we will write x, y, z. And this is actually, this is plus, this is actually is equal to 0 as per the continuity equation. So dou uj by dou xj is 0. So you get 2 mu dou squared ui by dou xj dou xj. So this is actually 2 mu into dou squared ui by dou x squared plus dou squared ui divided by dou x2, it will be y squared plus dou squared ui by dou z squared. So that way this 2 mu into, this is actually del squared of ui. That is the ith component of del dot tau transpose is 2 mu into del squared ui. So thereby del dot tau transpose is 2 mu into del squared of u vector. So like that we can change the we can modify the equation. So let us again take this. So this we can substitute. This we can substitute over here. That is okay. There is a half is also there. So that will be, so there is a half here. So there's a half here. Actually, epsilon is del u transpose plus del u by 2. So there is a half everywhere. So this will go. This 2 is not there. So this 2 will be disappearing. 2 is actually not there. It's a mistake actually. This 2 is not there. So we have mu del squared u vector minus 1 by rho del p is equal to dou u by dou t, dou u vector by dou t, plus this also we can do. This also we can do a little bit by doing the index notation. So ith, we will write ith component of del dot u u equal to dou by dou xj of uy uj. Actually this is one uy, this is uj, and for the ith component we take dou by dou xj. So for the ith component we write like this, dou by dou xj. So this is equal to this is product. So dou ui by dou xj into uj plus ui into dou uj by dou xj. So this we have seen that this is equal to 0 continuity equation. So this becomes uj dou ui by dou xj. So So, okay, this is ith component of ith component. Okay, so we'll write this. So J will be varied. So U1 is U, dou Ui by dou X plus U2 is V, dou Ui by dou Y plus U3 is W, dou Ui by dou Z. So this is actually we can write U dot del of Ui. So this is ith component. So the total vector del dot u will be u dot u dot. Okay, del u1 is one component. So the u dot del ui del u del u1 is u into ui plus u dot del u2 is v, the component the unit vector is j, u dot del w k. So you can take u dot del of ui del of ui plus vj plus wk, that is u dot, that is u dot del of velocity vector. So like that we change this we again take this one. So del dot, so it is u dot del of t. Okay, this is a form. Form. So this is actually like this. So we normally we write as dou u by dou t plus u dot del u is equal to minus 1 by rho del p plus okay, there is a 1 by rho is missing, 1 by rho started missing, there's a 1 by rho over here. Here del dot rho transpose only, so 1 by rho is not there, substituted, so 1 by rho is there. So this has a mu, so 1 by rho, this becomes mu. So from this point onwards, that is mu is kinematic viscosity. Mu is equal to mu by rho, that is kinematic viscosity. Kinematic viscosity. So we will have that. So this is changed into mu. So mu del squared mu. So this is what is called the momentum equation. Okay, this is the momentum equation. By considering this is the viscous term, so therefore it is Navier-Stokes equation. So this is what is Navier-Stokes equation. So when we generally talks about Navier-Stokes equation, which is the governing equations of viscous fluid motion, but we also write continuity equation also along with the momentum equation. So the totally Navier-Stokes equation, it means it includes the continuity equation also. That is del dot u is equal to 0. That is this entire simplification of Navier-Stokes equation is done for incompressible flow. Now, because we have taken certain simplifications of incompressible flow, that Stokes equation itself we have taken for incompressible flow, and we have taken sometimes density as a constant. So thereby this is applicable for incompressible flow. So this is incompressible Navier-Stokes equations. Now that this is actually a vector form, in vector form, and this is coordinate free also, because it is in terms of del and vector. The vector you can write in terms of different coordinate systems. So the components can be different for different coordinate systems. So we have in Cartesian coordinate system, the u vector is ui plus vj plus wk, whereas in the same u vector we write as ur er plus u theta e theta plus u z e z in polar cylindrical coordinate system. And we have the del operator is equal to I dou by dou x plus j dou by dou y plus k dou by dou z. It is caps. This is for the del operator for Cartesian coordinate system. And the same thing is er dou by dou r plus e theta by r dou by dou theta plus e z dou by dou z for polar cylindrical coordinate system. And we know that er and e theta are having the gradient spatial variation in theta direction. So these two things has got dou by dou theta which are not equal to 0. So dou er by dou theta, actually dou er by dou theta dou er by dou theta is equal to e theta, and dou e theta by dou theta is equal to minus er. So these kind of relations are there. So spatially er and e theta is varying in the tangential direction for the same radius. You take the partial derivative with respect to theta, we are going to have these non-zero Radials. So you have to simplify, or we can simplify this, or we can write down the expanded form of these equations by applying the velocity vector in the respective coordinate system and del in that coordinate system. So we have different expanded forms. So I like the expanded forms. NS equation in Cartesian coordinate system. Cartesian coordinate system. Oh. Okay, this is our vector form equation. Vector form equation is dou u by dou t plus u dot. So when you do that, so this for the u by dou t plus u dou u by dou x plus b dou u by dou y plus w dou u by dou z is equal to minus 1 by rho del p x. The I component is dou p by dou x plus mu into dou squared u by dou x squared plus dou squared u by dou y squared plus dou squared u by dou z squared. So this is for the x component. X component. So we will have certain modifications. So only thing is that we will be having same thing, this u to this u, this u, this u, this x will change, this will change, this will change, this will change. So this is b, this will become b, become b, this will become y. So this is for the this is x component, this is y component, and the so the this one would become w W, W, this is Z, this is W, this is W, this is W, this is W, and this is here, this is W. So this is the Z component. And continuity equation is dou U by dou X plus dou V by dou Y plus dou W by dou Z equal to 0. So this is the momentum equation. So the expanded form of Navier-Stokes equation for the Cartesian coordinate system. Similarly, for the polar coordinate system, we are having the components u r, u theta, u z. The velocity components u r, u theta, and u z. And the corresponding to this, the continuity equation is dou u r by dou r plus u r by r plus u r by r plus 1 by r dou u theta by dou theta plus dou u z by dou z equal to 0. The first momentum equation is the radial momentum equation, radial momentum balance. Is dou u r by dou t plus u r dou u r by dou r plus u theta dou u r by r dou theta plus u z dou u r by dou z. And I told the same thing. This is the temporal acceleration, and this is the convective acceleration, and you know, we are considering the tangential motion of the fluid particle that will produce what is called a centripetal acceleration, that is given by u theta squared by r. Actually, this comes out of that gradient of er and e theta with respect to theta. When you do that simplification, this will emerge. The centripetal acceleration will emerge. So all these terms will be coming out. So actually, physically, there is a centripetal acceleration that will be coming as a result of mathematical simplification when you do it. So that is a simple mathematics. You just have to apply the gradient, and we have to apply this u dot del u. You have to find out for the respective respective the gradient operator and velocity vector in the respective coordinate. So that has er, e theta, everything. And that er is differentiated with respect to rho theta, the terms will come. So that is a mathematical simplification. And coming to the right hand side, we are having 1 by rho dou p by dou r plus mu into Laplacian, that is dou squared ur by dou r squared plus 1 by r dou ur by dou r plus 1 by r squared dou squared ur by dou theta squared. This is the Laplacian of ur, and because of the derivative of the radial and tangential unit vectors in the theta direction, we will get two more extra terms. That is ur by r squared minus ur by r squared. So dimensionally you can see also. So there is a ur, and the denominator there is r squared. Here ur, r and r, so r squared. So this is also ur by r squared. Again, that is velocity component and r squared minus 2 by r squared dou u theta by dou theta. So these give certain equation. So this completes the radial momentum balance equation. Similarly, I can copy this and try to complete the expanded form of expanded form of what is called the tangential momentum equation. So tangential component, tangential momentum. Okay. So we change this will change, this will change, this will change. So this there will be modification. So I change this out. So this will change, this will change, this will change, this will change, this will change. So dou u theta by dou t. So this is dou u theta. This is this u theta. U theta. So instead of centripetal acceleration for the radial direction, the acceleration in the tangential direction is what is called Coriolis acceleration. The Coriolis acceleration is due to the combined effect of ur and u theta. So it's going to be ur u theta, and that is positive in the anticlockwise direction. For positive ur and u theta, it is going to be it will be accelerated in the anticlockwise direction. So you will have plus sign for that. So this is r dou theta will come. So this is this I will just so this is u theta, this is u theta, this is u theta. So this is u theta, this is ur, and this is both. So this kind of this is tangential momentum. Then axial momentum is straightforward. Momentum. Axial momentum will not have all these extra components. Extra things are not there. So we'll have this one, this one, this one, this index and is not there. Nothing corresponding to that is there. So this will change. This will change. This will change. This will change. So this is not there. These extra terms are not there. These extra terms are not there. So we have like this. So let us write this Z. This is 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 Z. So this is the axial momentum equation. So